Welcome. In this video, what I want to do is talk to you about piecewise functions, and I want to talk to you about some common misconceptions that students usually have with piecewise functions. And I'm going to do that by providing you four false statements and then showing you a counterexample that kind of shows that those statements are going to be false. So the first statement is going to be that all piecewise functions have either jump discontinuity or a hole. And this really kind of comes into our instruction with piecewise functions. A lot of times we just deal with them having some sort of a jump, or having them a piecewise function with a hole of some sort, right? But that doesn't always have to be the case. You could also have a asymptote in this case. So for instance, one time we look at a function, we could deal with the reciprocal function, and then looking at the logarithmic function. So you could have an infinite discontinuity with piecewise functions. Usually, sometimes this might not be as common, but just remember, just looking at where these functions are defined and undefined, and seeing their behavior is going to determine the type of discontinuity that they are going to have. Or the functions could also be continuous. A lot of times we deal with discontinuity so many times that students, just feel like every piecewise function is discontinuous. And that's not true. They can be connected here, so they are continuous, meaning their domain is going to be all real numbers. The next one is all piecewise functions are defined for all real numbers. So I guess I was talking ahead of myself. Yeah, and that's exactly the case. We look at discontinuity, discontinuity, discontinuity. And you can even have a discontinuity, like with a hole, which we kind of talked about in another video, where it has a defined value. So just because a piecewise function is, is going to have a discontinuity doesn't mean that it's not defined for, all piecewise functions are defined for all real numbers. Oh, actually, this is the exact opposite. A lot of times when we're dealing with them, we feel like they are going to be defined for all real numbers. But you can see here, you could have a hole like this where it is defined for all real numbers. But if I, well, actually, we wouldn't really have that in a piecewise function. But when I deal with a piecewise function that has a infinite discontinuity, the function then is not defined for all real numbers. Or another one that doesn't come up as much, but it's just important to know, is a lot of times we deal with discontinuities in piecewise functions at the same kind of value. However, we could have a break in something. We could have there's the function, and then the next function doesn't start until the positive value, right? So therefore, there's a gap inside the domain. So the idea of piecewise functions are defined for all real numbers, comes from a lot of the functions that we deal with, often. A hole that is defined, a jump that is defined, or piecewise functions that are continuous. But they don't all have to be, like those examples. They can be undefined at their discontinuity, or just a gap between them. The next one says the value k that makes the function continuous is the value of the vertical shift between the two functions. And this one kind of comes up a lot when we're dealing, with a piecewise function. And, we look at, I don't know, x squared, plus 4. And then this one would be 3x minus 2. And we say, oh, sorry, not x4, but let's make that the k. Okay. And actually, let's put the k. Sorry, let's do that as a plus 4, and then let's put the k here. K plus 4. Okay, so you could say x is less than 1, x is greater than or equal to 1. So when we want to find the value k, right, we set the equations equal to each other, we plug 1 in for x, and then we solve for k. And a lot of times what we looked at is these two graphs, k is basically the vertical shift and everything. But k doesn't have to be that always just the vertical shift. In this case, you could see k could represent the, the slope. So it's not always just, if you have two functions, for instance up here, if I want to make these two functions continuous, I'm basically just vertically shifting up and down, those two functions, right? But it's not always just a vertical shift. And the way that a function would look here, if it was not a vertical shift, I'll use a different function. Let's say it's x squared plus 4, same thing, x is less than 1, but now let's put the k here. So kx, let's say plus 3 or something. So now k is representing in the slope. So now it's really directed as far as how steep or down do these two graphs need to be for them to be continuous. Now, I did not check my work here as far as I just made these examples up. The main important point that I'm working on here is that the value of k because I'm trying to see if these would be equal, like what exactly my answer would be. But the important thing is k does not always have to be the shift up and down. It can be also, you know, in different portions of the equation. But again, the idea is still the same. You're going to take the value, you're going to set the two equations equal to each other and plug in the value of x in for, or the value of your, you know, your domain restriction for x, and then solve for k. The next one is piecewise functions are never even and odd. And this one happens a lot. We don't really deal with a lot of piecewise functions that are even or odd, meaning, remember, piecewise, an even function is going to be symmetrical about the y-axis, and odd function is symmetrical about the origin. And this doesn't really come up very much because we're usually dealing with piecewise functions that, you know, are very interesting, taking on a lot of things. But remember, if it's even, it just has even symmetry. So, you know, it can look like something, you know, like that has, you know, symmetry. Or if it's like a quadratic with a hole, and as long as the dot above it, you know, is there, that graph has symmetry. A function that is odd, meaning it's symmetrical about the, you know, symmetrical about the origin, right, could look something like that. And, you know, you could have like some kind of, you know, there it's symmetrical about the, you know, origin. So it's not very common, but that doesn't mean that it doesn't exist. So I had a hard time thinking about the piecewise functions as far as the, you know, statements that'd be false. So I'd love to kind of hear some of your comments as far as maybe some misconceptions that students have or you have with piecewise functions, and ones that we can maybe create a counterexample to kind of show they are, you know, false. So I'd love to see your comments and look forward to what you guys come up with. Cheers.